All right, I see a lot of people aren't here, so we'll take attendance. Extra credit. Uh, so last time we talked about the Turing Test. We talked about early instantiations of robotic stories by Isaac Asimov in the 40s. This was years before electronic computers were invented, back in the mid to late 40s, early 50s. Asimov laws of robotics kind of drove those plot lines. We talked about robotics in actual real life use. So this is not science fiction, this is science fact. As early as World War I, we had these killer apps, robots roaming around battlefields. This was a century ago, amazingly enough. This is before integrated circuits, before computers. There was already automation of various types. Today is much more sophisticated. These are autonomous robots roaming around, heavily armed, both on the ground, in the air, and there's Predator drones and Reaper drones flying, for days on end. They have huge ranges and heights and capabilities. Some are hovering craft, helicopters, drones, quadrocopters. Of course, now you can buy these things at Toys R Us for $50. Some are small, the size of insects, and some are seaborne, some are submersibles. They dive. These are all autonomous. Then we talked about the DARPA Grand Challenge, trying to come up with an autonomous vehicle. For years they failed until they crowdsourced it. They put $1 million bounty on it. After billions of dollars failed to produce results, and for $1 million or $2 million, they finally got it to work back in 2006. Several teams finished the DARPA challenge, created autonomous vehicles. Lots of AI, lots of sensors, LiDARs, radars. So these are pretty cool Turing machines. So this is only 12 years ago, and from there we got the Tesla Model S to this day. Only a 12-year period, actually 8-year period. This came out 2013. So very short gap between prototype to full commercial product. And of course in space we had robots and AI all along. Carl Sagan, the famous astronomer who wrote Cosmos, the famous TV show, basically was a big proponent of robotics in space and space exploration in general. And in space, you almost have no choice. It's so far away. Humans will not survive the trip, and those that do may not be able to come back. So it's very tricky business. So robotics is really a must. AI is essential on Mars and beyond. It's about half-light hour away. So if you want to send a message to your vehicle that's on Mars, the rover or whatever it is, have it reply to you, that's an hour round trip at the speed of light. So there's no time for real-time control. It has to be robotic. It has to have AI on board. It has to be autonomous, and has to know what it's doing and sense the environment and do intelligent decisions and so on. Otherwise, it'll be long destroyed by the time the message comes coming back saying I'm about to, fall into a crevasse or down a canyon wall. In factories, we have robots building almost everything that we consume, including computers, including other robots. Those robot arms build themselves. They build other robot arms. Around the house, you have automation already in the form of automatic vacuums and other automatic robots that can do various things. Sony has a pet dog called the Aibo. It's a robot dog. It can do simple things. So robots advanced quite a bit in the last 10 to 15 years, 20 years, by leaps and bounds. There's robots that assist paraplegics going upstairs. There's exoskeletons you can wear. And I think we left off with this contraption here. It's a robot surgical device. It's a surgeon. It's a robo-surgeon, and it can go into your body and make little tiny sutures, and through very small incisions do major operations without having to crack open the patient and risk infection and complications and so on, which is pretty good. Of course, there's always doctors on hand to supervise and make sure nothing goes terribly awry. And this is the Da Vinci system. It costs about $1.5 million, and many hospitals actually already use this. Some students have actually, some of our own students have actually worked on the system before and the software for it and so on. There's entire conferences on unmanned systems, on robotic systems, and some get very specialized. This one here is about underwater unmanned systems, not just robots, but robots underwater specifically. not just flying robots or roving robots or space robots. And then it's interesting to compare how reality is matching up with these science fiction scenarios that we saw earlier. So Captain Kirk in the 1960s Star Trek series had this little communication device that he opened, made a little twerp and told Scotty to beam him up and all that. And then about 30 years later, in late 90s, Motorola had a phone called the Star Tech, not Star Trek, Star Tech, but it looked exactly like this. Pretty much, you flipped it open, and later there was one called the Razor, again a flip open kind of phone. Today, those are gone. This is like several generations later, i.e., 10 years later. They're mostly flat tablets like the iPhone. Now everybody's copying the iPhone, but these flip phones were very, very popular just about 10 years ago, 15 years ago, and they were modeled after the Star Trek device. Now, they even surpassed the Star Trek device because today's smartphones cannot just call somebody, but you can shop from them, you can watch videos from them, you can tweet from them, send text, you can take pictures with them. It's a camera, it slices, it dices, it does everything. Where Captain Kirk, all he can do is call Scotty, on his device. So, that science fiction scenario was way, way, way underestimated. The reality just came through about 30 years later, pretty quick and much more impressive than the actual TV show and the movies that succeeded it. The Apple iPhone, by the way, has got a 1.8 gigahertz processor. If you can compare it to the Cray 1 supercomputer of 1975-76, the Cray 1 was 80 megahertz computer, 4 megabytes of RAM. This was a supercomputer. It weighed 5 tons. It consumed 200 kilowatts of power and cost $8 million. So if you compare the iPhone to that, it's an improvement of almost 400,000 times as far as power per cost kind of ratio. And even more than that, if you include inflation, the $8 million were 1976 dollars. That's like 20 or 30 million dollars today. So you're basically walking around with supercomputers in your pocket or your purse, and they're not just a little bit better than the supercomputers of the 1970s. They're millions of times better in terms of speed and processing power and cost effectiveness. So again, reality here exceeded science fiction scenarios by leaps and bounds. And in other things too, in the movie 2001: Space Odyssey, we had HAL 9000 beating the astronauts in chess. Today it sounds trite, but at the time it was almost laughable to suggest that computers will beat the best humans in chess. Well, fast forward 30 years, poor Garry Kasparov, world chess champion, is looking very despondent here, losing to IBM Deep Blue in competition rules chess. It was televised internationally, and so just to give you an idea how far computers have exceeded this movie in terms of chess playing capability, chess master is basically top 2% of tournament player on the ELO chess scale, rated 2300 roughly. Grandmaster is 2500. That's the top 2% of 1%. 1 in 10,000, 2 in 10,000 players are exceeding 2500 on the ELO scale of chess ratings. Super Grandmasters are 2700. There's only about 3 dozen in the entire world, humans that can play at 2700 level chess. Only 4 of them can play at 2800, including Kasparov, who peaked in 99, and the best human ever was Bobby Fischer in 72. He played at around 2900. The best player now is Magnus Carlsen. He's right up at Bobby Fischer kind of level. Computers now play at 3340. This is an exponential scale, and no human has ever exceeded 3000 or 2900 for that matter. So now your iPhone can play grandmaster level chess and beat most humans, all but maybe 2 dozen humans on the planet, right out of your iPhone. No extra processing or memory needed. It's quite amazing how far we advanced in terms of chess playing. So again, another example where reality far exceeded science fiction scenarios depicted in movies. And there again is Kasparov during that competition, 1997, Deep Blue beating him flat. And there were media storms about that. There was even a movie made about this documentary called Game Over. No feeling, no fear, no contest. It was very highly dramatized. Newsweek had in '97 a cover story called "The Brain's Last Stand." As they try to make it even more dramatic than than it really was. But it was dramatic. It was a turning point. And then a few years later, 2011, IBM Watson beat the world champions in Jeopardy, and not just by a little, but by a lot. You can see from these scores, he's scoring more than the two of them put together, basically. And Jeopardy is harder than chess in some sense, because you got to do AI, you got to do natural language recognition, you got to do speech processing, and so on. It's a lot less constrained than chess. Chess is very, kind of myopic, constrained, very precise game. Here, there's a lot of things that go on that are very hard to capture algorithmically. And then fast forward a few more years, and AlphaGo just beat the world champion just a couple of years ago, in 2016. And Go was thought to be a game that computers will not be good at for decades or even centuries, because the board size is much, much bigger than chess in terms of the game tree. So it's 19 by 19, or you can play even on larger boards, but the board size makes the game tree exponentially larger than chess. The game tree for chess is like 10 to the 60, 10 to the 70 nodes, where every node is a board position. And in Go, it's a Google times worse than that. It's like 10 to the 170. So it's not just a million or a billion times more difficult than chess. It's a Google times more difficult. So I guess that's probably, stands to reason, because Google created AlphaGo, and this game is a Google times more combinatorially difficult than chess. So there's Lee Sedol, the reigning world Go champion, losing to AlphaGo, and he's kind of sweating it. There was $1 million purse here, so he had not just $1 million reason to win, but he didn't want to lose his title as the best player on the planet. He's still the best human player on the planet, but not the best player on the planet anymore. Now the best player on the planets are machines. So again, that's another example where reality surpassed science fiction, and in other things they're catching up. In Minority Report, Tom Cruise was driving a self-driving car, or being driven in a self-driving car. Will Smith in iRobot, again, self-driving car. They look pretty slick. And 2005 we saw these prototypes full of sensors and kludgy kind of lidars and retrofitted parts, and of course now they're a lot slicker than that. So reality is really catching up with science fiction in the realm of self-driving car. And other realms too, Rosie the robot in the Jetsons in the early 60s. Now we got Roombas, and we got other household robots. There's one that cleans gutters called the Luge. Again, this is nothing new. It's 10 or more years old. There are specialized. There's robots that clean pools, and robots that can cook you pancakes or whatever. But there'll be a great convergence in these things, just like iPhone converged a lot of other appliances, right? In the old days, when you want to hear a song, you turn on your stereo system. If you want to watch a movie, you turn on your TV. If you wanted to send text messages, you do it through your computer. If you wanted to go shopping, you'd have to go to a shopping mall or to a store. Now, from your iPhone, you can do all these things and a lot more. So there'll be a convergence too in hardware, and there'll be more general-purpose machines that can. There are less specialized than these, and this is bound to happen in the next 10 or 20 years, as well. Other areas where reality catches up with science fiction, in Terminator movies, you saw these early T-100s or T-105s. They look like little mini tanks with threads and machine guns hanging off of them. Well, in reality, now we got the exact same thing. We got these real-life Terminators. These are products, and they roam around. They're autonomous or semi-autonomous. They got weapons on them. They got fully automatic firepower. They got sensors, lidars, radars, infrared vision, cameras, a lot of AI on board, and they can go off and do arbitrary missions. And some of them have solar cells that can be charged in the sun and not lose battery life. And so again, this is where reality is catching up with science fiction. Reality on the right, science fiction on the left here in these slides. We had in one of the Terminator movies, we had autonomous Terminators looking like motorcycles, basically two-wheeled vehicles. And in reality, we had that too. Even in the ARPA Grand Challenge, one of the entries was an autonomous motorcycle that not only had to cover ground and do smart things and traverse routes efficiently, but also balance so it doesn't fall over at the same time. So it's a quite interesting problem in control theory. Again, in Terminators, we had hunter-killer, flying drones, and we got those in reality too. And we got really amazing ones, Reapers and Predators, and with Hellfire missiles, and they fly supersonically. In the movie Stealth in 2005, there was a autonomous AI drone that can land on aircraft carriers, and sure enough, today we got the same thing. We got supersonic drones that can land by themselves on aircraft carriers as well as do other clever things around the world. So again, this is all about reality catching up with science fiction and catching up pretty quickly. In the movie Aliens, Sigourney Weaver playing Ripley had this power loader exoskeleton. How many have seen that movie? It's pretty cool. Well, we got those too now. We got exoskeletons that can enable you to carry hundreds of pounds of weight on your back. It's not really on your back. It's the exoskeleton doing the heavy lifting, and not your spine. So humans can now walk quickly with huge heavy weights because they have exoskeletons that they can wear. The ultimate exoskeleton, of course, in the movies is Iron Man. The suit is an exoskeleton, is a wearable robot. Really, the human is just inside. We got exoskeletons as commercial products now. There's a company called Cyberdyne. If you remember, the Terminator company in the movie was called Cyberdyne. It's no accident probably. And they make an exoskeleton that'll amplify your power by 5x. And it weighs only 50 pounds, runs for about 5 hours on a battery charge. The batteries are embedded in the exoskeleton. It costs $60,000. And if you can't afford to buy it, you can rent it for $600 a month. That's quite affordable for, an exoskeleton. That's pretty empowering. Not quite the Iron Man suit, but they're not done yet. So again, this is all about seeing how reality is catching up with science fiction on various domains. In the movie Logan's Run, there was a robotic doctor. It was up here with all the little appendages and scalpels and laser beams and surgical robot system, 1976. And of course, 30 years later, we got the Da Vinci system. And we already mentioned that. It's $1.5 million. You can buy it. Hospitals now use it quite a lot. So it even looks kind of similar in terms of the geometry of these appendages and robot arms and servo motors and so on. Captain Kirk was trying to steal some cloaking device from the Romulans. How many even know what I'm talking about out of curiosity? Okay, one Trekkie in the audience. That's good. So cloaking devices were the stuff of movies, and even Harry Potter had a cloaking, invisibility cloak back in the day, and now we got those too. There's prototypes of cloaking devices. There's even ones that you can wear as a cloak, as a real cloak. It's not quite 100% invisible, but it'll camouflage you pretty good. Just like that Predator in the movies, had this big, interesting camouflage function in his spacesuit. There's these meta cloaks that basically route light around the object and redirect it through where the object is. So if you stand on the other side of the object, you're seeing the light source unimpeded as if the object wasn't there, which essentially renders the object invisible for practical purposes. And they're working on it for different wavelengths, and so even there's huge advances. So the gap keeps narrowing between science fiction and science fact, and in some cases, the science fact has far exceeded the science fiction. We already see examples of the iPhone and chess playing and Go playing and that kind of thing, and this gap is narrowing quicker and quicker. So this cartoon is one of my favorites because it just happened a few years ago, where it just shows you, tries to kind of human trying to hang on to some things that only humans can do. Like it says, only a human can translate speech, or only a human working can clean a house, or only a human can review a movie, and so on. And more things are on the floor now crossed out because machines can do them, right? Only humans can pick stocks, and machines, algorithms can now pick good stocks, and so on. And when this cartoon came out, look at this one. It says only humans can drive a car. So this cartoon already became outdated, so I had to update it by putting a little red cross through that one as well. So even a cartoon like that has a very short half-life because technology is moving so fast, and very soon other things here will drop to the floor until there's very little left, if anything, on the wall as things as only humans can do. But again, we still don't know exactly where all this is going. We don't even know what's intelligence, what's mind, consciousness, self-awareness, sentience. These are kind of nebulous terms, but they're not nothing, because a lot of what we do as humans kind of hinges on these things. And in some ways computers have far exceeded us, other ways they're catching up, in other ways they're still a little bit behind, but it keeps improving all the time. So it's kind of interesting. The technological singularity is an interesting concept, invented by Ulam and von Neumann back in the 50s. And the idea was that when machines become intelligent enough, they'll do whatever it is we humans do, and perhaps more. And one of the things humans do is invent other machines, like the ones on your desks and in your pockets, the iPhones and the Dell computers and the smartphones and the tablets. And once they do that, they will invent bigger and better and faster and more efficient and more effective versions of themselves, which will keep doing the same thing. And there'll be a feed-forward loop. There'll be, I guess you can call it a virtuous cycle as opposed to a vicious cycle. And once this happens, it'll happen quicker and quicker, and it can get to lightning speed. There can be a new generation of machines every single day, or every 5 hours, or something like that, as opposed to every 2 or 3 years, like we have with our own computers, because we humans are slow and sluggish. These things are not. They're very agile and fast. And once this happens, it can sort of take such large speeds and progressions and improvements that humans looking at this thing, at this process, may not even understand what's going on. It'll happen so fast and so out of our realm of understanding or comprehension or speed to process them as humans that we'll basically be bystanders in this, spectators in this process, and that could be interesting. And so this feedback loop will bootstrap itself, and you'll have some sort of intelligence explosion. And we may be left behind. Now, that's not necessarily a bad thing, but it could be a bad thing. It depends how it happens and what the consequences are, which again is not clear, right? You can have scenarios like in Terminator, or you can have kind of utopian scenarios where none of us will ever have to work again. The machines will provide everything. The whole notion of job may become obsolete. I mean, why do we have jobs, and why do we even have money? Because there's not enough stuff around. There's not enough food and clothes and shelter, and so we have to ration it. And money is a way of rationing things. It's like coupons, right? What's a job? It's a way to make sure that everybody does their fair share. Why? Because some stuff needs to get done. That if we don't do it, society will collapse. Well, if machines do all that stuff, we won't have to, and there'll be no such thing as jobs and money and wealth, and everybody that needs something immediately will be provided with that thing. Machines work for free, and they're much more productive and effective than we are. So that could be one scenario. Another scenario is, Terminator. That's the other extreme, where we'll be very sorry we ever, allowed this to happen. So Ray Kurzweil calls this law of accelerating returns. Other people refer to it more darkly as gray goo. If you saw the movie The Day the Earth Stood Still, the one with Keanu Reeves, the old one I think was better, but the new one was okay. But basically there was nanobots, and they self-replicate, and they use everything around them as raw materials to create more copies of themselves. Basically the ultimate virus. So the entire Earth was in danger of becoming one big mass of gray goo made of just solid, trillions and trillions of nanobots that would use everything around them as raw material to build more nanobots. Some of the raw material would be us. Humanity will not have a good day if something like this happens. So that's the so-called gray goo phenomena. Transistors per microprocessor grow at exponential rate. That's called Moore's law. But Ray Kurzweil makes the point that Moore's law is not just about transistors growing exponentially, doubling every couple of years, but also processing performance grows exponentially. These are all exponential curves. These are exponential scales here on the y-axis, and across the x-axis is just time, the last few decades. That's it. And so average transistor price drops. It used to cost like $1 or $2 per transistor. Now it costs like a nanodollar or a picodollar per transistor. They're so cheap that you get billions of them on a single chip in your iPhone. Microprocessor cost per transistor cycle, again, dropping exponentially. So there's all these Moore's law going simultaneously. It's not just the Moore's law. It's just one of many improvements, exponential improvements all over the place, all across technology. Dynamic RAM price, bits per dollar, exponentially improving. Magnetic disk storage, exponentially improving. I remember buying a disk in 2000, was it 1985 roughly, It was a 40 megabyte drive. It cost me $1,600, $1,600 for a 40 meg drive. At the time, it was the biggest drive you could buy commercially. Unless you were a large corporation, when the drives were the size of refrigerators. Of course, today it would be laughable. No drive is even less than 100 gigabytes or 500 gigabytes, even, and those cost just a few bucks. I have flash drives in my pocket that carry 64 gigs. So a 64 gig drive looks like this now. Actually, this is probably 128 gigabytes. So things have improved by orders and orders of magnitude just the last couple of decades. Internet traffic has increased exponentially. Supercomputing power is increasing exponentially. Again, these are all analogs of Moore's law. And the gene bank data is increasing exponentially. Even the number of U.S. patents granted is increasing, dramatically. That dip here, what would you guess that is? The dip in patent applications. World War II, yeah. So human strife is not good for innovation, not to mention human lives lost during these wars and conflicts. Milestones are interesting. Here life started on Earth about 1 billion years ago, and then the first mammals, and then dinosaurs extinct, and then Homo sapiens emerged. And this is an exponential scale here on the x-axis. So things are happening faster and faster by these milestones, right? So for the first 1 billion years of the Earth existed, nothing much, if interest, happened. At least not interest to us. Very little change, qualitative change. But then humans came around, and we started, recorded history. We invented, tools, and we invented the notion of government and democracy, and we had a renaissance, invented the printing press. But now the difference between these milestones is only centuries. And then we had the Industrial Revolution a couple hundred years ago, the steam engine, finally modern physics, and then invented the transistor, and then the computer, and then iPhones, and all that happened just in the last few years, and social media. So now we're talking about years span, not even decades. So it's exponentially accelerating in terms of milestones, new milestones that completely change the landscape. And now things are changing extremely fast. Most of you remember the time before social media. That was only 10 years ago, right? I mean, how did you share photos? How did you keep track of your friends? How did you communicate, family news to other family? Well, somehow we managed, right? But it seems almost unthinkable to do it now without social media and YouTube and all these other devices and capabilities and mechanisms that we created. And in 10 years, probably YouTube will, and Facebook will be completely obsolete, and there'll be something else, replacing those. So things are changing very, very quickly. It's sort of coming to a head. It's asymptoting into something that is both interesting and somewhat alarming at the same time. And Ray Kurzweil calls this a singularity. So some people are already augmented. Some humans have a pacemaker in their chest. A pacemaker is not just some clunky, primitive device. It's a full-on computer with an operating system running hundreds of thousands of lines of code. Your pacemaker could be running Linux. It's a full-threaded operating system and multi-processed, and it can communicate to the outside with Bluetooth or Wi-Fi, and it's part of your body now. And some people have chips in their heads that allow them to see when they were blind before, or allows them to hear when they were deaf and couldn't hear before. And these computer chips are integrated into our brains now in various instances, usually medical applications. And some people just have chips in their bodies implanted for other purposes than medical assistance. And that will, some people have, artificial joints, artificial spleens, artificial, kidneys, or artificial other devices in their bodies, And so we don't think of them any less human because they have these augmentations, technological augmentations. In fact, they may have more capabilities than the rest of us, some of them. So Kurzweil saying, all this will kind of accelerate and become more dramatic, and technology and humans will merge and integrate more and more until they become indistinguishable. So if you look at computers, we used to be the size of auditoriums, the size of buildings, in the 60s and the 70s, big mainframes costing millions of dollars. And then it became smaller and became mini computers the size of refrigerators. Then it became smaller yet, and it became computers that you can put on your desks, like these boxes here. And then that was 20 years ago, 1990s, early, mid 80s, early 90s. And then we had tablets, which are even smaller, laptops, and computers became smaller yet, and now they're the size of iPhones, and the smartphones are in your pockets. You can see where it's going. And Google Glass had glasses, and the computer is inside your glasses now, and the whole thing is completely self-contained in the rim of your glass. How many have seen Google Glass or heard about it? You can see where the next logical step is, and it's already happened. It just gets embedded into your brain directly. And when it does, you don't need a keyboard anymore, and you don't need a screen anymore. And the keyboard and the screen are the two bottleneck components that force it to be large, because our digits, our fingers, aren't going to get any smaller. So the keyboard's not going to be like this. It's got to be this big, right? And the screen ain't going to be one little square millimeter. It's got to be something that you can actually see. But if you can dispense with these peripherals and have direct brain interface, so you don't need keyboards and screens and other big things, you can have a very tiny thing that just augments your mind. And if you want to multiply two very large numbers together during casual conversation, you can do that instantly by, outsourcing it to the little chip in your head, as opposed to trying to do it using the protein part of your brain, which is not very good at arithmetic. Or if you're in a job interview and you want to look something up on Wikipedia, you can do that just with a thought, right? Because you're Wi-Fi enabled. Your brain now has its own IP address. That's pretty cool, pretty impressive in an interview. So he's saying that's sort of where it's going, and we can see a lot of evidence, for that hypothesis all around us. It's getting more and more so. And these epochs the universe went through. First is basically the epoch of physics and chemistry. Supernovas spewed out, heavy elements from which stars were created and solar systems. And then biology started taking over. Large polymers, molecules began to self-replicate and created viruses, and then bacteria, and then multicellular organisms, which then became larger and more sophisticated, and brains developed right here in the third epoch. Neural kind of organisms, and then us neural-based kind of creatures with brains developed in the more synthetic technologies, computers and smartphones, and now AI and whatever is next. And then it's starting to merge with us. And the fifth epoch, and by the way, these epochs are getting shorter and shorter. The DNA, the physics and chemistry epoch was like 10 billion years, maybe 12 billion years. The biology epoch was only 1 billion years. This brain epoch was only a few tens of millions of years, maybe a few 100 million years. Dinosaurs had brains, not very big, developed brains, but still brains nevertheless. And then, of course, technology epoch is only a few 100,000 years, beginning with Stone Age stone tools, not very sophisticated stuff. The Iron Age, the Stone Age. So that only a few tens of thousands of years. And then, technologically speaking, most of the action happened just in the last 50 years. I mean, computers were just, electronic computers only existed for 60 or 70 years now, since the 1950s. That's it. And things are moving faster and faster. So there's exponential increase in speed, and these epochs become shorter and shorter. And once humans and computers merge, which could happen in a few decades, that's it. The universe will become, this kind of super intelligence will spew out into the universe, in a sense of space probes and terraforming robots going out to other star systems and so on. And maybe it's already happening elsewhere, and we just haven't seen the wave coming in the opposite direction, But this could easily happen from our direction to the rest of the universe. It's already happening. We're already sending, robotic probes, to far reaches of the solar system and beyond. And this is just the beginning. We just started doing that recently, so we haven't even gotten that far yet. So that's sort of the hypothesis of where he says this is going. It's called the technological singularity. It's pretty cool to contemplate. We are sort of right here between technology and the merger of technology with humans. And we're just a few decades away from this, dramatic mergers, or more dramatic mergers. We already talked about mergers occurring. Computers are already inside humans in various ways, and it's getting more and more so. So that's the idea. But it's not without alarm or warning that this is hypothesized. We already talked about gray goo phenomena, where nanobots can run wild and use us all as raw materials for their own purposes, mostly self-replication. This is kind of a joke, but a sign you might see in the future. Only you can prevent gray goo. Never release nanobots assemblers without replication limiting code. Right? Just safety first. Right? There's already books called Nanotechnology for Dummies. When you see a book that's just like X for Dummies, whatever X is, it means X has gone mainstream, whatever it is. Now you probably have books called Quantum Computing for Dummies, and so that's kind of interesting. There's some people who are sounding warning bells, and justifiably so, because these kind of technologies and possible futures have a lot of potential for good, but also a lot of potential for harm if something goes terribly wrong. Because of replicating and highly efficient and super fast, if something goes wrong, it'll go wrong big time, not just a little bit. Genetics, the same thing. This could be some really bad scenarios when you start messing with genes, but also some good ones, right? They can prevent birth defects, and maybe you can increase human intelligence and prevent, certain diseases like diabetes and things like that. If you can turn on and or off the right genes, that will be good. And Bill Joy famously wrote a Wired article called Why the Future Doesn't Need Us, and he's basically an alarmist about these things. But he's no slouch. He co-founded Sun Microsystems and co-authored Java, basically co-invented the language Java. But he basically says that robotics and genetic engineering and nanotech are a threat, or a potential threat, and we can become endangered species, just like we turn other species endangered because of our actions or inactions. It needs to be taken seriously. And other people said, it's a bit too pessimistic. There's some rebuttals to this, saying it's not all doom and gloom. We can put controls in the loop. We can kind of watch what we're doing. We can develop. What's that beeping sound? Don't know. It doesn't have to be bad, and there's a lot of potential. But we do have to be cautious. There's also potential for harm as well as good. So that's another article. You can read it at your leisure. It's pretty cool. And there's a Singularity Institute for AI. It meets, like every year, basically. There's Ray Kurzweil. There's other luminaries that meet and talk and hypothesize and discuss these things and try to come up with remedies and plans how to get there and what to do along the way so it doesn't become a disaster for the human race and so on. It's called the Singularity Summit. There's the 2009 meeting here, but it happens quite often, and it has very interesting and smart, accomplished people. Stephen Wolfram is one of those typical speakers at these things, and Peter Thiel, who co-founded PayPal and Facebook, is also one of the supporters and advocates of these meetings and these kind of hypotheses. So it's pretty interesting. So if you want to know more about these things, I included in the slides a bunch of links to wiki pages and other pages, so you can follow up if you want. It's pretty cool stuff. Any questions or comments about any of this? So this is kind of potential future scenarios, seeing the trends, extrapolating where it's going, or at least trying to. It's hard to predict the future. The famous saying, it's hard to make predictions, especially about the future. It's easier to predict the past, right? Because it's already happened. In this course, aside from talking about all this cool stuff, we talked about the Chomsky hierarchy, and this picture kind of captures most of the technical material of the course. There's a lot of complexity classes and relations among them, decidable, undecidable things, the halting problem, and so on. And remember, we started with Aristotle. It's interesting to start a computer science course with Plato and Aristotle and the Greeks, but I wanted you to see the big picture, end to end, how we got from abbacus to smartphones over a 2,300 year period. And but now you should be able to talk, for long periods of time about any aspect of this of this diagram. Explain it to your friends, or kind of think about what you know about these complexity classes and language types and their interrelationships and machine models that correspond to these complexity classes and and language types. And there's a lot going on. And this is just the tip of the iceberg. Remember, we looked at the complexity zoo diagram, which was a lot more involved and detailed, containing hundreds and hundreds of classes, not just a few dozen classes. I made a list of stuff that we covered in this course, and I alphabetized this list. Concepts, ideas, proof techniques, and starting with 2 sat and 3 sat, and I'm highlighting in red a few ones that are just kind of interesting to point out. But we covered most of these things, not just the ones in red font. We talked about algorithms a lot. Talked about approximations, asymptotics, axiomatic method, cardinality arguments. There's captures, the Chomsky hierarchy. We just saw that again. Boolean functions, various properties thereof, the Church-Turing thesis. So this is just a list to show you all the stuff we covered. All the ideas, proofs, concepts, techniques. We talked about most of these things quite a bit. Complementation of languages, completeness classes, compositions of functions, Cook's theorem. Right, proof by contradiction, context-free languages, the concatenation operator and its effects on different language types, lots of proofs by counterexamples. Right, we talked about dovetailing and diagonalization. Boy, we got a lot of mileage out of these two just by themselves, as I promised we would. They were involved in dozens of different proofs if you think about them. Denseness of the hierarchies, space and time, and other computational resources consumed. Decision versus optimization versions of problems, like playing 20 questions, how you build an optimizer from a decider using 20 question type algorithms or approaches. That's what this is. Deciders versus recognizers. De Morgan's law, we got a lot of mileage out of that in many proofs. Cross-product constructions, like how do you cross machines and get the intersection of regular languages or other machine types by crossing them with other machines. That's cross-product construction. And look, we're over 100 concepts, and we're only on D now. This is alphabetized, yeah. 110. 110 was, Dedekind cut. All right, since you asked, I think we mentioned that early in the course, but it's a way to define real numbers. So each number class that's bigger than the previous one can be defined strictly in terms of it. So natural numbers are the counting numbers, 1, 2, 3, 4. Integers are naturals plus their additive inverses, the negative ones. So notice how you define integers strictly from natural numbers. 0 is the unique integer that's its own additive inverse. And now you could build rationals from integers simply by taking quotients. Now you can build real numbers from rationals by taking Dedekind cuts. So Dedekind cut, with this introduction, is take all the, say if you want to define pi, take all the rational numbers less than pi and all the put them in one set. Take all the rational numbers bigger than pi, put it in another set. These pair of sets uniquely define pi. You can do the same thing for any other real number, square root of 2 and e. And so that's a Dedekind cut. So basically you go whack, with a very sharp knife on the number line, take all the rationals here, all the rationals there, 2 separate sets. Now you got real numbers, strictly defined as a function of rational numbers. Here's the next leap. To define surreal numbers, you can still do it with a Dedekind cut, except that you don't have the constraint anymore that all the numbers in the first set are smaller, strictly smaller than all the numbers in the other set. They can be mixed together like this. 2 arbitrary sets. And that's called a surreal number. And those things, some of them are not real numbers. They're surreal numbers. But just like some real numbers are not rational numbers. Just like some rational numbers are not integers. Just like some integers are not natural numbers. And so on. So that's where Dedekind cut comes in handy to define higher and higher, more general sets of classes of numbers. Good question. So going on, well, that's an interesting segue, right? Elegance in proving. We talked about that many times, right? Occam's razor. Simpler is better. Time and space complexity classes, enumerating sets, Existence proofs, again, I'm just harping on the red ones, but I just arbitrarily highlighted a few red ones just as a sampling. From Maslow's theorem, Chomsky hierarchy, finite automata, formal languages. We talked a lot about these things. Gödel's theorem of incompleteness. Every formal axiomatic system is incomplete if it's at least as powerful as arithmetic. Generalized finite automata. That was handy to show regular expressions are equivalent to finite automata. Game of life, that's a cellular automata, specific instance of it that Conway invented in the 70s after von Neumann invented the general concept in the 40s and 50s. Grammars, we talked a lot about context-free grammars, context-sensitive grammars. We're almost up to 200 and we're just on the G's. Graph colorability, graph isomorphism, we talked a lot about that just the last 2 lectures. The halting problem, we beat that one to the ground many times. Prove its undecidability, and now from it you can prove other things are undecidable. And talked about heuristics and approximations, hierarchy theorems in space and time, Hilbert's problems, specifically his 10th problem, which said every polynomial, every recognizable set is Diophantine. There's a polynomial that corresponds to it, so polynomials can compute. We didn't know that. And of course, lots of historical perspectives. We talked about incompleteness, incompressibility of strings just in the last assignment or 2. We talked about why induction is not the first choice of proving things, although you should know it. Infinite hotels and applications to cardinality, countability, uncountability, infinite hierarchies of infinities, intractability. We talked about interactive proofs just last time, zero knowledge proofs. Clean closure operator and its effect on language classes and applying it to certain languages and strings and other things. Lexicographic orders came in handy many times to prove cardinality arguments or lack thereof. Machine enhancements, trying to enhance Turing machines or finite automata with different things like multiple tapes, bigger alphabets, multiple heads, the ability to use non-determinism and so on, and the effects of these enhancements. So again, this is all stuff we covered in this course. We talked about many one reductions, right? We talked about non-determinism a lot. All of NP-completeness revolves around non-determinism, right? Non-existence proofs, like proofs that I'm not a millionaire. It's hard to do. NP-completeness, of course, one-to-one correspondences. There's Occam's razor. We talked about that a lot. Lots of open problems, not just P is equal to NP, but hundreds of other open problems like NP is equal to P space, NP is equal to co-NP. We don't know. They're all open. There's many more open problems than problems that have been settled actually in complexity theory and crypto. Oracle computations, hyper-computations. We mentioned that. That's Turing's one of his many other contributions. Dovetailing simulations, P versus NP, pigeonhole principle. We got a lot of mileage out of that one too. Pigeonhole principle. Innocent-looking principle, but very, very powerful. Polya's book, How to Solve It, very useful in becoming a MacGyver. Polynomial time versus exponential time. Power set constructions. Right? Bertrand Russell's Principia Mathematica, where you axiomatize all of mathematics on the back of set theory. Basically, it's a reduction. It's a reduction of all of math to set theory. We didn't realize set theory was that powerful. That you can do calculus using sets, analytic geometry using sets, and topology using only sets and nothing but sets, and so on. Or do statistics using only sets. That's pretty amazing. So set theory, in some sense, is the machine language of mathematics. It's the zeros and ones of mathematics upon which everything else is built. P-space, polynomial space, we talked about that. Rational numbers, in fact, we just mentioned it a few minutes ago, answering your question. Real numbers, same thing. Recognition and enumeration, various reductions, regular expressions, Q automata versus stack automata, resource-bound computation, that's complexity theory, lots of classes there based on consumption rates of resources, space and time. We mentioned that space is reusable, and that has interesting repercussions in terms of proving things about complexity classes and their relationships. We talk about Rice's theorem, how it's a very pessimistic result, showing that most things they can think of, most properties of languages are not decidable other than the two trivial ones, where all languages have that property or they don't. One of the most pessimistic theorems I've ever seen, actually. Terrible negative result. Robustness of P and NP, Russell's paradox, right, that Pinocchio with his nose saying, my nose will now grow, and of course that was the crux of many other proofs. For example, Turing's undecidability of the halting problem relies on a version of Russell's paradox. Satisfiability, 3 sat, the general sat, and so on. Savage's theorem, relating space, non-deterministic and deterministic space. There's only a quadratic relationship between them, where in other classes it's exponential. Of course, we harped on the scientific method all along, talked about self-replication, right? Lots of simulation type proofs and theorems where something simulates something else, and therefore showing an equivalence between the two. Talked about spanning trees, minimizing states, lots of things about strings and superstates when you have non-determinism converted to determinism for finite automata. I talked about time and space hierarchies and trade-offs between space and time. If you have more time, you can use less space, and vice versa. You can trade off one resource against another at your option. Talk about tractability or lack thereof. All of NP-completeness is a study of tractability, right? Talk about transfinite arithmetic, Hilbert's hotels, and how to make one-to-one mappings or lack thereof between one set and another set, showing generalized cardinality arguments. We've had questions like that on the exams even. Traveling salesman, triangle inequality, that came in handy a few times in proofs and in arguments. Turing degrees, we talked about that when we talked about Turing, hyper-computation, oracle-based computations. You could play what-if games. If you had an oracle for the halting problem, then what can you do with that? And that's the whole premise of Turing degrees. And of course, Turing machines, that's talked about that a lot. The Turing Test, we just talked about that today and last time. Two-way finite automata, uncomputability. So there's a lot of stuff. And this list isn't even exhaustive. Zero knowledge proofs, we just finished that last time. And this, I could probably double the size of this list. So we covered a lot of ground here in this course in just about 14 lectures. It's quite amazing what we covered if you think about it. But the one thing that permeates everything that I want to impress upon you, both in terms of this kind of material and generally in life and in science in general, is quoting Einstein: make everything as simple as possible, but not simpler. Don't add complexity unnecessarily, whether you're building a theory or looking for laws of physics or building a car. That's one of the reasons that electric car is so much better than a gas operated car, because it has so much fewer parts. Sometimes I ask people, what's the most reliable part in any machine, in any device, in any program? What's the subroutine in your program that will never fail, never go wrong, never take too long? It's the one that ain't there. It's an interesting conceptual way of looking at things. So an electric car doesn't have a transmission, so the transmission will never go wrong. When I take my Tesla to get a state inspection, which you have to do every year, I jokingly tell the mechanic, just don't tell me I need a new muffler, because there isn't a muffler there, right? So he kind of giggles nervously, thinking that probably in 5 years he will be out of a job, because there's hardly anything to fix aboard an electric car, right? But anyway, Occam's razor is what this is. Simpler is usually better, and that's sort of one of the basic concepts that kind of permeates through everything we did in this course. And of course, we started with Aristotle and Plato, and then we went forwards, and everything kind of is influencing everything else. So it's all about influences. Every sort of great thinkers of one era influenced the ones that succeeded them, and they kept building up on that, and here we are, with supercomputers in our pockets, and it's not done yet. We're just starting, basically. We're just beginning. The thing about exponential curves, most of the dramatic effect happens in the very last few doublings, not earlier on than that. Right? There's a famous, kind of math riddle that says, you have a pond and you have a water lily growing. It's doubling every day in terms of size. It's growing very aggressively. After 30 days, it covers the entire water pond. And what day did it cover half the pond? Day 29. But a lot of people will say day 15, which means they don't understand exponentials. Most of the exponential explosion happens very, very recently in any exponential process. And we're on an exponential curve. As you saw from all these charts and data that Kurzweil showed, Moore's law all over the place. And which means in about 10 or 20 years, we won't even recognize, the technology. All this will seem extremely primitive. All these computers on your desks and smartphones in your pockets will seem so archaic. It would be almost embarrassed to admit you've ever used them. Of course, now they seem pretty cool, but same with the Apple I came out in the 70s. I had a TRS-80. That was the coolest thing in the world, a Radio Shack TRS-80 computer back in 1979. Ran BASIC. You just typed in commands. And it ran. You didn't have to go to some, university or government installation and use a building-sized computer using punch cards. You can actually type it on a keyboard. They would run instantly. That was pretty cool then. Now it's very nostalgic, but same thing will happen over and over and over again. It's called progress. Anyway, any questions or comments about any of it? So this kind of caps off what summarizes what we talked about the last 3 months here.
Do you think there's like a 2 steps forward, 1 step back scenario where we've got engineers who no longer have that hands-on basic experience that you just described?
Yeah, so occasionally there's setbacks and sometimes there's dead ends. And even in technology, there's dead-end products, right? The Apple Newton, is an example. There's all sorts of, even Google Glass, that didn't last very long. For whatever reason, they pulled back from it. They're probably rethinking it, redesigning it. But and engineers, so technology gets more and more complicated and esoteric, and it's hard for anybody to be a generalist anymore. People are myopically focused on very niche things. So there's people who, for their entire life, all they do is, work for Microsoft writing device drivers, for printers and, disk drives and CD-ROMs. And I wouldn't want to be one of them, but I mean, it's a living. They make $100K a year or more, doing that. And some of them know nothing else but that. So they're very, very specialized. But that's kind of a dangerous trend if everybody was like that, very, very niche-y, specialized. So I try so one of the things I try to do in this course is give you a very wide, broad perspective. I could have omitted, 2/3 of things on the list. I didn't have to tell you about the Greeks and Antikythera, computers that the Romans had, and I didn't have to tell you about Gauss and Euler, and I didn't have to tell you about Dedekind cuts, or surreal numbers. I didn't have to do any of that, and it would still be a fine theory course. But it's important to see the big picture, especially how we got here to this day, from abbacus to iPhone over a 2,000-year period, and all this stuff in between. And some of it was steps backwards or missteps, or occasionally you get some big blunder. Hiroshima and Nagasaki were probably, 2 big blunders, along the way of understanding physics better. And there might be more coming, and, they might be pretty dramatic, right? Everything has a dark side too. Everything could be used for negative effect as well as positive effect, right? So nuclear power is great until a nuclear bomb goes off, and then you see that, there's a flip side to everything. Right? Facebook seems wonderful until somebody uses it to throw off an election, or to troll people, or drive them to suicide, by bullying them or trolling them. That happens too. Doesn't mean Facebook is terrible in its absolute sense. I mean, cars are mostly good. They get us from point A to point B efficiently, quickly, cheaply. But every now and again, some deranged person gets behind the wheel of a car and drives through a crowd and kills people. It just happened in Toronto just like a week ago. How many heard that? Happened in Europe many times. So people are using cars as terrorist weapons now. But the reaction shouldn't be, well, let's ban all cars then. Cars are evil. They're not evil. It's just we have to find ways of making sure people can't use cars as deadly weapons, as 3,000-pound missiles, plowing through crowds. Now, it just so happens if that car was smart, it wouldn't let that driver plow through a crowd. It would stop and tell the driver, "I'm sorry, I won't let you do that." Smart cars. So smart cars are answer to a bunch of different things, not just that. But yeah, it's important to keep the big picture in mind. Basically, you don't want to specialize and become too niche-y, embroiled in something and ignore everything else, including consequences of the technology that you're developing or working on. Crypto has a lot of good applications, but also, terrorists can use crypto to communicate and plan and plot without the authorities being able to track what they're doing. So everything has a flip side. Bitcoin is mostly good, except when drug dealers are using it to sell, large quantities of illegal drugs, and hitmen are using Bitcoin, or people are using Bitcoin to hire assassins and things like that without any attribution and any way of tracking it down. And so that's another thing to keep in mind. The ethics of engineering is becoming more and more important. And and the more powerful our technology, the more important this is. If you're going to create technology that will create nanobots that can self-replicate, the ethics better be right up there in the front of how it's going to be used and who's going to be using it, and safety mechanisms and controls and so on. You can't just throw it out there and say, hey, it's a free-for-all, and just grab it and use it. 3D printing is a whole revolution unto itself. So for example, 3D printers, you can print arbitrary objects now, and some enterprising guy, this is actually several years ago by now, printed a gun, a fully functional automatic weapon. How many heard about that? They printed, so it's not that hard to do. So of course the U.S. government got upset, the ATF, the people who tracked and register guns and track their serial numbers and give licenses to people who want to buy guns and so on, got so upset with this, because anybody now can print a gun in privacy of their garage, and nobody can track it. So one senator got up and kind of wrong-mindedly said, oh, if you can use 3D printing to print guns, let's ban 3D printers. Which is kind of idiotic. So right after he said that, within days, some hackers got so riled up by that statement, that misguided kind of mindset, that they created a 3D printer that can print 3D printers. And now 3D printers are self-replicating. So you can't ban them. They create many copies of themselves now. You can't even track that. Never mind the other things that they can build. So, it's hard to put the genie back in the bottle. In fact, you can't on certain things. So all the more reason we need to be kind of cautious and thoughtful and mindful about what it is we're doing, and keep the bigger picture in mind. You can't just ignore it all. It's dangerous. It's unwise to just not worry at all about ethics, and because it can come back and backfire in a big way. What else? Yeah, so another thing I wanted to show you is, then we'll take a break, and then we'll have a Q&A, Ask Me Anything session. Science, math, and money. So it turns out that if you look at the money of different, the currency, the bills, the legal tender of different countries, usually you see very, interesting things, because the people and ideas depicted on the money, shows you the priorities and mindset and what, countries are considering important and significant and so on. So U.S. money is pretty boring by comparison, but other countries' monies include, famous scientists, philosophers, engineers, mathematicians. So here's the Israeli lira, now shekel, showing Albert Einstein, for example. But I kind of compiled the list of a sampling of other countries' monies, and some of it is really fascinating to watch, because some countries only show politicians on the money, and usually they're not even just any old politician. It's white male politicians, and it's not particularly interesting. So here's a sampling of other people's currencies, other countries' currencies. So Carl Friedrich Gauss is shown on the German marks, and in fact, you see the Gaussian distribution, the bell-shaped curve is right there, and the equation is correct, actually. So it's unusual when you have a pretty deep mathematical expression involving exponentials on a currency. So that's a nice example of not underestimating your population and their ability to understand things and inquire and appreciate things. In the U.S., I just don't see that happening for whatever reasons, especially nowadays. But I digress. So On the back of the Deutschmark, there's a sextant, an instrument that's used for navigation, kind of historically. And on the Swiss francs, there was Leonhard Euler, the father of graph theory, and on the back there was some inventions by him and observations by him and so on. By the way, some of these are before the euros, so the euros kind of made the money much more boring across Europe. But some countries like Switzerland never converted to euros. They just didn't want to abandon their beautiful money with all the meanings on it, and for other financial reasons. But so on the British pounds, you got Lord Kelvin, who pioneered thermodynamics, and Michael Faraday on the 20-pound note, who pioneered physics and electromagnetism back in the 1800s. And so it's like a lesson in science. And every time you pull a bill out of your pocket, it's interesting. Sir Isaac Newton, again on the British pound, on the 1-pound note. There's Einstein again on the Israeli shekel, and there's Galileo Galilei on the Italian lira, and again, he shows other things, inventions. Here's an astronomical observatory because he was one of the early astronomers who founded modern astronomy and so on. And there's Marconi on the Italian lira, again before the euros, but he invented basically the telegraph, the telephone, right up there with Alexander Graham Bell, and some early renditions of these instruments are shown on the back. Pretty interesting, very respectable. You can basically give us, a whole science lecture on each one of those, individuals and their inventions. There's Volta on the Italian lira. The volt is named after him, the electric potential. There's the Greek drachma and Democritus. He lived in 200, 300 BC, and he invented the notion of atom. In fact, the word atom means indivisible in Greek. And so the Greeks knew about atoms. They just couldn't prove them. They just couldn't see them because they didn't have, microscopes, strong enough and experimentation kind of decisive enough to actually empirically prove their existence. But they postulated that this indivisible unit of matter called the atom, and atom in ancient Greek means indivisible. And there's Democritus who pioneered that notion back 2,300 years ago on the money. He was right on the money. No pun intended. He was correct. So Nicholas Copernicus appears on the Polish zloty. Again, he one of the early people that showed that the Earth is not in the center of the universe. Much to the dismay of the church, who put people like him under house arrest or worse, sent them to the Inquisition or tortured them or killed them or burnt them at the stake while they were still alive. Him and Galileo and others, Bruno, and so he gets a lot of homage on the money too. And there's Marie Curie, and she invented radium, or discovered radium, and pioneered the study of radioactive isotopes and radioactivity in general. And there's only a few people, maybe 3 or 4 people ever, that won 2 Nobel Prizes. Not 1, but 2. And she's one of them. And she won it in 2 different fields. The other ones won like 2 times in chemistry or 2 times in physics. She won 1 in physics and 1 in chemistry. It's an amazing individual. She got a lot of crap during her life for all sorts of things, including being a woman. Back in the turn of the century, when women were not respected very much in the sciences and the engineering fields. And even today, we're not quite at parity yet. Up to modern present day, we're not quite there yet, but we made a lot of progress on that. So she's a hero to everybody, not just women, but men too. Chopin appears on the Polish zloty. We all heard of him, right? One of the greatest composers of all times. And on the French francs, Marie and Pierre Curie were appearing both. So she appears on multiple countries' currencies, not just one, which kind of mirrors her 2 Nobel Prizes. She appears on many currencies. And there's René Descartes on the French franc, again pre-Euro times, and Pascal is on the French franc as well. And again, you can have entire courses about their philosophies and ideas and how they influenced others, and we talked about them here too. So it's pretty cool to see money that's actually interesting and scientifically significant and pays homage to people who made a huge difference, in for the human race and for our scientific advancements and the way we live today and so on. Pasteur, he appears on the French francs as well. Voltaire, same thing. Money was prettier than those days. Uh, so let's see what we got here. We got Schrodinger on the Australian shilling, pioneered the atomic theory of matter and quantum mechanics, and Rutherford, Lord Ernest Rutherford, also great physicist, on the New Zealand dollars. So this is very impressive, actually. Paying homage to the people who really really deserve it. Nikola Tesla appears on the Serbian dinar, right? Tesla Model S is named after him. He invented the motor that Elon Musk is using in his cars, actually, among many other things. He pioneered electrical theory and magnetic flux and Faraday cages and so on. So there's Nikola Tesla also on Yugoslavian dinar. Here you could look at the denomination. It's pretty amazing. It's called hyperinflation. When you got 10 billion dinars in one currency, and hyperinflation is fascinating because I carry with me just for times like this. This is a $100 trillion note. This is a real note. It's a Bank of Zimbabwe, though. It's not U.S. dollars. So I'm a trillionaire 100 times over in Zimbabwe dollars. I'll just pass it around. If you're thinking of stealing it and retiring, in Zimbabwe, this will get you a cup of tea. Not even coffee, just tea. So that's what hyperinflation does to money. But it's kind of cool to see. Now entrepreneurs from Zimbabwe are selling that on Amazon for $5 or $10 as a and it's a much more worth as a trinket for $5 than the actual face value of the money. But anyway, that's the Yugoslavian dinars showing Nikola Tesla, and he appears on other currencies as well. And Niels Bohr appears on the Danish kroner. And again, Bohr pioneered early atomic theory and early physics and chemistry, and he was a contemporary of Einstein and Schrodinger and Fermi and all these others. A pretty impressive guy. This guy we talked about too, Abu Ali al-Hassan, an Iraqi dinar. He was known as the physicist. Remember we talked about him? He wasn't a physicist, he was the physicist. There was only one physicist on the planet, and he was him. This is the year roughly 1980 or whatever it was. And he gets a lot of credit, not in this country, but elsewhere in the world, for doing what he did so early on. It took centuries and centuries for people to even understand what he did and then reinvent some of it from scratch, because there were a lot of dark ages and many centuries of lost time and lots of political turmoil and wars and genocides and a lot of lost opportunity to the human race. But he was there early on. Too bad that people didn't continue his work after he did his stuff, because we probably would have cured cancer and been to Mars by now if we didn't lose so many centuries to inquisitions and crusades and holy wars and all sorts of other nonsense. Sigmund Freud appears on the Australian shillings. He basically invented modern psychology. Before him, when somebody had mental issues, people used to think that they're possessed by demons and dunk them in ice water or lock them up or beat them or try to get the demons exorcised out of very primitive, atrocious kind of behaviors. But he put psychology on a modern footing. And there's Charles Darwin on the British pounds, and when Richard Dawkins came by and gave a talk a few years ago, he tried to make the point between England and the United States. One of the differences between European countries and other countries is that they embrace Charles Darwin right on the money and pay homage to evolution, while we sort of take the other approach. With that, I'll just leave it at that. Any other thoughts or comments or anything like that? Oh, that thing, I don't even know. But I'm sure it has some significance. Anybody know what this pyramid is with the eye on top? It's on your dollar bill. It's on all of our dollar bills. I mean,
So it starts from Babylon time. That represents like in Abel's time, people trying to build like a tower that is super high.
oh, the Tower of Babel.
Yeah. So nowadays you see lots of buildings in that shape because they represent something like the rebellion of God. Um,
Okay.
like the monuments in Washington,
Yeah.
pyramids everywhere.
Yeah. The obelisks.
Oh yeah, probably.
Yeah. Okay. Fine. Yeah, it's kind of. But you're right. It is kind of mysterious, right? Um,
I heard something like conspiracy theory.
what's that?
Conspiracy
Oh,
theories.
conspiracy. Yeah, there's also conspiracy theories. Yeah. I mean, there's no shortage of that these days. Uh, all right, so let's take a break and then we can come back. We can have an Ask Me Anything session, and also, I'll answer questions about the homework, the last homework. If you have any questions about any of the problems on the homework, I feel in a generous mood. We can go over some solutions or ideas, or any other questions you might have on technical things, or anything else for that matter. So let's take a short break and come back in 15 minutes.